Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So as we're all experienced enough researchers to know that when someone like me gets up and starts talking, that I'm actually presenting work that was done by other people and I just talk. So it turns out if he's in the room, if you have any questions, one of the students who was on this project, Amar, you might direct all questions to him instead. So I'll start out with a pop quiz. What's that? People in this room can't answer that. Oh, wrong answer. I updated my slides just for this talk. That is a Microsoft data center in Dublin. Normally I show a Google data center because that was when I made the slides. But the Microsoft one's really pretty. So it turns out that when you build a data center in Dublin, you get to run your air conditioners on completely passive, non-chiller, no compressors mode 95% of the time, which is one of the reasons other than taxes and politics and all sorts of other considerations that cause you to build a data center like this in Dublin, because it saves you enormous amounts of energy. So over the years, I've come on a kind of this three-legged model of data centers and energy. If you've got 1,000 watts of servers sitting in a data center somewhere, the first thing you do is you stack a bunch of chillers on top of it, like we just saw, in order to make them not melt. And you add UPSs and power generators and things like that so that they keep running when bad things happen. And all of that is just overhead. It's not going into the computers that we know and love. Now, in the bad old days, those generators and chillers and all that stuff might have drawn something like what I have there, approximately a factor of 2 as much as the computers themselves did. So the industry got together and it said, hey, we need a metric for this. We'll call it PUE. And high PUE is bad. And it turns out, over the years, these numbers have come crashing down if you are talking to the players who really know what they're doing. So Microsoft and Google and Yahoo and Facebook these days have achieved PUEs of like 10% overhead, 1.1, 15%. So they only spend about 15% of their power doing that otherwise unnecessary junk. Now, the problem's not gone, because if you go down the street to your friendly neighborhood hospital or financial corporation who does not have the resources and clue of a Microsoft, their PUEs are still embarrassing, and someone ought to help them do something about it. But it's not really a technical research problem at this point. It's a people problem. Second problem in power is proportionality. If you've got those 1,000 watts of servers and you run them at 20% of their peak load, they may draw 50% of their peak power. You look at that and you say, well, that seems a little bit wrong. And well, yes, it's wrong, but it's an engineering challenge. My view on this is people like Intel and Dell and folks have been making slow progress on this. But when academics come along and say, well, I've got a great solution for you. We'll just turn off the computers when you're not using them. People at places like Microsoft and Google kindly take us academics aside and they say, psst, we have to pay for those computers. It's CapEx. You're telling me to waste my investment. So if there's anything revenue positive that you can do with those computers instead of turning them off, figure out what to do with them and do it. I don't care if it's running SETI at home or something like that, but do something instead of turning off this $1 million pile of junk. So I've been spending less time thinking about proportionality. And what we've been spending all of our brain cycles on for the last couple of years is thinking about energy efficiency. Why does it take 1,000 watts of energy to get done the job we wanted to do in the first place? What can we do to make it take less? So there are many approaches to solving this. But there are two things that we've looked at a lot. The first one is that gigahertz is not free. If you want to run faster, it takes you more energy per multiplication, per addition, per basic operation. This graph is a lie, as many such graphs are, so take it with a grain of salt. The y-axis is energy efficiency. Higher is better. This is the number of instructions that you can execute per joule of energy. The x-axis is speed. These are turtles, these are Lamborghinis. You'd love to be on the very upper right of that plot. You're super efficient and you're super fast. And you'll note that no one's there. The reason it's a lie is I gave everybody an Ethernet interface that draws some power so that these little 8-bit microprocessors look like dogs, because we don't want to be programming dogs, because developers actually cost money too. But so the interesting thing about that is there's a very definite sweet spot in energy efficiency. And you are all carrying a device that operates in the sweet spot of energy efficiency in your pocket. 1.2, 1.6 gigahertz, depending on how much cooler you are than I am. a gig of RAM, things like that. And it's not coincidence that your cell phone operates right there. So that seems like a great way to save some power. We'll just run on slow processors. There's a second reason, which is very familiar to all of the database people and all of the architects in the room. Things like the memory wall and the increasing gap between our ability to read things off of storage. Computers keep getting faster and faster and faster and faster, which means that when they have to go to memory, they're really bored. And so we start adding all sorts of magic. Caching, speculative execution, prefetching, yada, yada, yada. And all of this stuff makes it so that we are not crippled by the memory wall. But it doesn't actually make our processors any faster. It just makes them consume a little more power. And then the second problem is that transistors at their heart, they look like little capacitors, and they behave like little capacitors. And when you want a transistor to flip, you put a bunch of charge on one side of it so that a bunch of charge carriers diffuse into that channel. And if you want that channel to flip faster, you put more charge there. So from a fundamental transistor physics perspective, it actually costs you more energy to flip your transistors faster. So you can either be patient or you can be energy efficient, but you can't really be both. And so from our research perspective, we've come up with two very cheesy, please forgive me, sounding pillars that we look at for building energy efficient systems. The first is that gigahertz hurts. And the second is that, remember, memory capacity costs you. And this actually gets back, I don't think Jan is here, to Jan's comment in the earlier session about bigger and bigger and bigger memory buses. So if you want more and more and more and more memory on your system, you put bigger and bigger and bigger buses. And those buses, you take more energy to get stuff across them. So if you didn't pay attention to anything I just said, cell phones are really efficient. Big, really, really, really fast servers are substantially less energy efficient. So we've been building these things. And that is what we affectionately call a fast array of wimpy nodes, or a FON. This is one of our more recent generation ones. We're software people, not hardware people, as you can probably tell. So this is a cluster of 88 nodes with 1.6 gigahertz dual core atoms, not that dissimilar from a cell phone. A gig of DRAM each, but unlike your Pocket, we give them very large amounts of very fast flash memory. And we've been asking ourselves, how do we build big data-intensive processing systems using these fundamentally energy-efficient systems? And what lessons do we learn about the world and life from doing that? So I don't think I saw Kathy in the room. So I can freely misquote her at my discretion. So Kathy Yellick's been looking at HPC for a long time. And she observed, broadly speaking, that every time you threw a factor of 10 more processors at HPC people, they had to toss out a whole lot of what they'd done before and redo it in order to extract even more parallelism out of the code. So that cluster that I just showed you of 88 nodes, if you're thinking about it, if they're like 8 times wimpier than a normal node, you're probably running 10 times more of these things in order to get the same amount of work done. So what I just told you about isn't free either. It is a way of trading massive amounts of developer and algorithmic pain for energy efficiency. So whether or not you actually like this approach in practice is a very good question. We can ask Vijay if he wants to really build it into his data centers or not. The answer is probably no. So I affectionately call all of this the Swan quad of pain. So because you have to build bigger clusters, you have to deal with more load balancing. You have to extract more parallelism. Because you're using wimpy nodes, you have less memory capacity on each node. And you find yourself with this burning desire to both avoid the quirks of the hardware and take advantage of any opportunities it offers, be that SIMD units or other thing, anything you can do to get a little more speed out. And the combination of all of that makes my grad students absolutely miserable. And it's great, because they do the programming, I don't. But unfortunately for all of us, this is not just masochism. This is in some ways a fundamental consequence of the hardware trends that we've been seeing over the last 10 years. So this thing is our very, very familiar and well-loved Moore's Law. It continues. We're continuing, although albeit at a slightly reduced rate, to get a factor of 2 increase in transistors per dollar these days, about 3 years. Awesome. But that's Dennard scaling. That was our ability to drop the voltage as we shrunk the process. And that stopped. And the consequence of that is gigahertz increase has effectively stopped. Gone are the days where we thought we would have 6 gigahertz processors on our desk. It's kind of gone gloop, because now everybody's trying to figure out optimized designs that are a little better here or a little better there. But basically, there's a pretty solid line there that just, we're not going to go up to 6. So I argue that all systems are going to face this challenge over time. And so one way for academics who don't have the budgets to build clusters of 20,000 nodes to kind of get an edge ahead and anticipate some of the pain is to voluntarily embrace it by picking weird, quirky hardware and doing some research to figure out how to actually make it useful. So we started this out with a key value storage system. Key value storage systems are ridiculously popular these days. If you look at something like Facebook, when you assemble your main Facebook page, they used to send MySQL queries to a backend MySQL server. This was when Facebook was still quasi-legally running off of a server in a Harvard dorm. That does not scale very well. So in order to improve that, they stuck a memory cache in between their big servers and their big MySQL servers that absorbed all of those hits. So each of those little SQL queries actually gets executed as an individual key value query. Hey, is the answer to this query in the cache? Yes or no? And it turns out you don't just do one SQL query. You do a heck of a lot of SQL queries. Somewhere between 100 and 1,000 queries, individual key value queries, are executed just to assemble your main Facebook page for you. So these things are very performance conscious. People care a lot about latency, a lot about throughput, a lot about cost. And they're random access, and randomness in computers, not so hot. Very efficient for sequential processing, but when you start to do randomness, particularly with disks, but even with flash, life starts to get a little miserable. So 2008-ish, we built this thing. And this thing did not use those shiny nodes I showed you. It used these 500 megahertz embedded communication motherboards that we found from some dude in Switzerland who was manufacturing them. They had extremely high-tech 4 gigabyte compact flash cards. We thought we were pretty cool. And the goal was to build a system that had substantially better energy-efficient performance in terms of queries executed, key-value queries per joule of energy. And it turns out that it was hard. It was a lot harder than we expected and required a lot more systems and algorithmic engineering. And that has been the story of our last 5 years. So wimpy CPUs, limited amounts of DRAM. As you're probably all aware by now, Flash is extremely poor at small random writes. It's very good at bulk sequential writes. It's quite good at small random reads, but it's absolutely atrocious if you want to modify a bit here and modify a bit there. And of course, when you build a big cluster out of these little wimpies, you'd like to make sure that life doesn't go to you-know-where when nodes come and depart. So as one example of the kind of solutions we had to create for this, or adapt, given that log-structured file systems were known for 20 years, the way we chose to avoid random writes was we took a straightforward log-structured approach. So we had an in-flash data region, we had an in-DRAM hash table, and whenever we'd put some data in there, we would just stick it in the end of the data region and update an entry in the hash table telling us, hey, key K1 is stored at this particular location on disk, so that we could read it randomly, but all of our writes were sequential. And we looked at that and we said, this is really cool, except we've only got 256 megabytes of memory on these nodes to store that index, and we're competing with, say, the operating system for some of that 256 megabytes. And so we came up with a new hash table design we called partial key hashing. And the idea took advantage of the properties of Flash. We basically created a hash table that could be wrong. But it wasn't wrong too often, and if it was wrong, we just had to do another read off of Flash. So 1 in 1,000 times we had to do 2 reads, but most of the time we sacrificed that small probability of being wrong for saving a lot of memory in the DRAM-based hash table. And then it turns out we've continued this line of research over about 3 or 4 iterations now, where we came up with a cuckoo hashing variant of it that saved even more memory. And then, of course, this is the days of parallelism and concurrency, so we also developed a concurrent version of that, actually a lock-free optimistic concurrent version of that we published just this year. I should say 2013. So it worked. In 2008, it was 6x more efficient than a comparable conventional approach. If you did this again these days, modern CPUs have become more energy efficient. I don't think you'd see 6. I think you'd see 2 to 3 times more energy efficient from using a really efficient processor versus a conventional approach. And we were actually able to use it to create fairly good, high performance, reasonably predictable key value storage services. And then time did what it does and it moved on. We moved to atoms and modern solid state drives. And if you look, these are the improvement numbers in CPU, in memory, and in both the speed and capacity of the flash drive. And one of those numbers is very different from the others. So while we got 6 to 8x faster and 6 to 8x more memory, flash drives took this amazing leap during that time period. And they got between 30 and 60 times faster and bigger. And so we thought we had been extremely clever in our memory-efficient partial key hashing design, and this forced us to throw it all out and go back and redesign something that used 1/8 as much memory as our previous design. In fact, our new design didn't even have enough memory to store a pointer in memory to where the thing was on flash. So the story thus far, we started out with FonDS and FonKV. We moved forward to atoms. We designed a system called silted SOSP. And in order to do that very memory efficient thing, we landed somewhere that, as a systems person, I would never, ever, ever have expected to land. We published a paper at Allenex, the Algorithm Engineering and Experimentation Conference. And I am so not qualified to do that, it's not even funny, but I've got really smart students. So Hyuntak came up with a scheme for external hashing, right? External, you use a little bit of memory to figure out where to read the thing on expensive external memory. That turns out to be the most memory efficient, practical external hashing scheme known to humankind. And I recently heard from conversations with some folks at MSR Asia that Bing actually is using, not for external, but what is the currently known best internal memory efficient hashing scheme known to humankind, a scheme called CHD. For some of their indexes. And so there's an enormous amount of opportunity for these kinds of advanced, but practical, focused algorithmics that are kind of at the cutting edge of conferences like Allenex to really have an impact on big data systems these days in a way that I'm not sure I appreciated until we got our feet wet on it. So I told you we were able to build well-performing systems using these WIMPs. I lied again. I seem to lie a lot, I'm sorry. And the way I lied is, of course, when you have a system like this with little Atom CPUs and solid state drives, you obviously cannot handle your entire workload using one of them. So you put a bunch of them together. And as I said, we have 88 of these things at the moment. And you use standard consistent hashing techniques, hash the key, figure out which backend it goes to, send the query to the backend, send it back to the user. So this is great. And you think, how does my system's performance scale as I add more and more backend nodes? And the answer is, well, it depends. So our goal, we'd love if each of those things can handle 10,000 queries per second, right? The system should provide an aggregate throughput of 880,000 queries per second. And we can scale that back, right? SLAs are important in these systems. We could say, let's get an SLA of 850,000 queries per second. Right. So the red line is the scaling performance as we increase the number of nodes. This is throughput. If the workload is completely uniform, this isn't even uniform random. This is round robin uniform among keys we know are designed to hit all of the backends. So if you want to lie, you can just show that graph and say, my system scales perfectly, unless you expose it to real world queries. A real world query might look something more like the blue line, which is a zip distribution, heavy-tailed. So on a heavy-tailed distribution, this cluster of ours achieves something like 1/10 or 1/20th the performance of what we would like it to. And if you've got an adversary generating your queries, in this case, it's the Lady Gaga workload. All queries go to Lady Gaga, no queries go to Dave Anderson, which is as it should be, but the throughput is exactly what you'd expect. It's the throughput of one node, because all of those queries are going to one wimpy backend. So our system had this extreme weakness under not even horrible, like real workloads. And so we looked at them and we said, wow, that's really unfortunate. Is that the end of the line for the Fawn research? And it turns out the answer is, Well, it was a little bit because we had to bring in some actual fast, high-powered hardware. So we added a cache to the front end that was doing the load balancing. And the big question is, well, how big does the cache have to be? If you've got to cache all the items in your back end, it's not going to be very useful. But it turns out there's this really cool duality between load balance or load imbalance and cacheability. If all of the queries are going to Lady Gaga, your cache has to have one item, and you've slammed everything out of your cache. If the adversary has randomly distributed queries over everything, well, your cache is useless no matter how big it is, but that's okay because the workload can be handled because it's perfectly uniform. And it turns out the answer is O of n log n. The actual answer is about 6 n log n, where n is the number of backends. So if you've got 100 backends, you actually only need to store a couple of thousand items in your front-end cache, and you can guarantee basically perfect load balance. Or you can guarantee that the load is so imbalanced that your fast cache is handling everything. And with only a couple thousand items in your cache, you can fit that cache in L3 cache on a big beefy microprocessor. And so where we ended up was with a system that used one big beefy in the way that a big beefy works best. It's not even touching DRAM. And a whole bunch of wimpies who are the ones who are sitting there going, okay, slow flash, please satisfy my data requests. And once you do that, life is really good. So the blue line is then the zip distribution, and you can't really tell the difference between perfect and adversarial because they're basically overlaid on top of each other. Adversarial is just a little bit worse because the worst case is you do it randomly, and our perfect case was, as I said, round robin. But basically the worst case becomes the best case, just with a small cache. Have I exhausted you all? Okay, so where, Catherine, please.
The theoretical cache work, how do you prove the number of items?
How do we prove the number of items? So remember, I'm faculty, I don't do the work. So the answer is there are actually two things.
At least understand the
It's just my name on it. So there are two aspects to it. We did it as a competitive analysis, and basically we said adversarial analysis. So we at the same time figured out what is the worst adversary or the best adversarial strategy, and what is the performance of that, and what is the bound. And it turns out that the adversarial behavior is the thing that picks Lady Gaga. And the power of that ends actually at about less than n log n. Because at some point you start forcing the adversary to distribute the queries over a suitably large enough. But the thing that actually causes the n log n is standard balls and bins caching. If you're just doing random balls and bins into these backends, then you're going to have an n log n, or sorry, a log n over log n imbalance. And that's the thing that actually causes the problem. And so we end up having to take n log n in order to compensate for the imbalance due to just standard hashing. So the adversarial part dropped out early enough that it was tractable.
Okay, so that says because of that distribution, you don't have to replicate the entire cache on one of the backends.
Correct. So now we can talk about how to add multiple front-end caches, which we haven't quite figured out. And there are a couple of really fun questions about extending this, like if you have better load balancing schemes, like if you duplicate all of your items in the backends once. I think we can do more to actually reduce that to actually n log n over log n, but it's like a factor of 3 savings, so I can't bring myself to care too much. Okay, so where I just took you on that whirlwind of the last 5 years of my life is that we ended up with a system that looked kind of like this. We've got this SILT thing in the back end using a very memory efficient index to figure out where stuff is on disk. Here's my third lie of the day. The algorithms that we developed for SILT are not fast enough to run well on the Wimpies. So we're still trying to overcome some CPU bottlenecks. In front of SILT, we've got an insanely fast cache where we prove the size of the cache necessary to guarantee load balance so that we're able to have a system that can create an SLA equal to the scaling of the number of Wimpy backends. As random fallouts of this, we ended up inventing the first multi-reader parallel cuckoo hashing scheme, that preserves the memory efficiency of cuckoo hashing. There's actually one from Microsoft that was earlier than we are, but we use less memory. And we had to come up with this AllenX thing for the best known practical external perfect hashing. So this has been an absolutely wild ride for us. And well, it's all the fault of the architecture people. So if I had one takeaway, it's that as systems and database people and things like that, there is an enormous amount of value in talking to these architects early on and saying, so what is it that you people are going to be doing to us in 10 or 15 years? And how can I figure out how to anticipate and solve those problems ahead of time? And the drawback is that the problems cut across every part of computer science known to humankind. It is architectures, it is algorithms, it's systems. This is some of the hardest programming that I and my students have had to do, and we would love more help from that. And we're just starting to bring in machine learning, but incredible fun stuff. Questions? Have I tired you all out? I'm done?
Okay, so yeah, questions?
Have you tried other?
There's a remote audience who wants to hear you.
So I think you focus on the storage or I/O intensive workloads. So from the key value and the later workload. So have you tried a little bit more applications in the data center and see how the phone nodes can work with other big servers to for example, search engine or video on demand system, something like that? How can it work in a real data center?
We've looked at a couple of other applications. So the core ones we've looked at is we just use search as a proxy for a large number of applications. And it turns out search is one where there's a really fascinating kind of pattern of interaction where if all else is equal, wimpy nodes are the same factor of 2 to 3 more energy efficient for doing search, except that the efficiency lines cross radically when workloads drop out of, say, the L2 cache in the wimpy, but they're still fitting in the L3 cache in the beefy. And then there's another drop when you leave the main memory of the wimpy and have to involve the network, but you can still fit in that terabyte of memory we were talking about buying in a single server. And so there are these stair-step functions that make the analysis really complex for real workloads because it depends on where you fit in that space. We also looked at the problem of multiple pattern matching, as you might see in things like virus scanning or intrusion detection and prevention. And that was another one where we were able to craft a solution for the wimpies that was substantially better. But to do so, we also had to go back to the algorithmic drawing board because the conventional multi-pattern matching solutions used too much memory to fit in the wimpies. So once we got things to fit in memory, it was fine, but we actually locked up our cluster by running every node out of memory once, trying to run grep. So the bottom line is there's a lot of efficiency to be had, but almost none of it is free. And it's taken anything from recompiling to completely re-architecting the software systems.
So I have a really quick question because I know I'm down here. So you said something which sort of intrigued me, which is, so the wimpy nodes are also, it's a moving target.
It is a moving target.
So same thing that you have with the high-end nodes, you have with the wimpy node. So
yep.
How does that, you get to the point where now you're not as efficient given the algorithm designs or whatever? I mean, have you looked at that, what that point is? In how many years do you get to that point?
Well, sorry, the point at which what is not as efficient?
So, you designed this nice load balancer to ensure that you talked about the caching strategies and things, and essentially to keep, you're going after trying to conserve energy, use lower energy with these lower processors, but, as for example, next talk, I don't know if Vijay's going to mention that, but we always have the generations of servers that we kind of move forward. Right? We have the high-end servers and we move them back. And they become very, very powerful. They're probably much more powerful than the wimpy nodes that you have.
Although you might be surprised, right? A cell phone is an incredibly capable device. But I think the answer for the long term is that in the long term, what I've been doing may become irrelevant, but hopefully we'll have created solutions that work in the weird world that we're going to end up in the long term. Because, right, for a while, when gigahertz was doing that, there was a very easy definition of wimpy. It was like, cut the gigahertz by a factor of 2 and cut the issue by a factor of 2, and you just track it. But now with the gigahertz leveling off, and we're seeing this very slow increase in things like the gigahertz and the capability of cell phones. And as that creeps up, I think the big difference will be things like cache sizes and core counts. And as soon as the only difference between a wimpy and a beefy is a cache size and a core count, and it's less about the gigahertz, then you have actually lost that fundamental gigahertz-based physics reason for the energy efficiency. But you've also got, 48 core CPUs that you have to program, and so everybody else has embraced our pain anyway.
Yeah.
So.
Okay, well, let's thank our speaker. Okay, our next speaker is Ratul Mahajan. Ratul is a senior researcher in the Mobility and Networking group at Microsoft Research, and he graduated from University of Washington and has won several awards in his very young career. And he's essentially going to talk a little bit about utilization of the bandwidth between data centers. So. And SDNs and software-defined networks and things like that. So very topical.
Thank you, Victor. So in both Dave's and Vijay's talk, we heard a focus on efficiency. And this focus on efficiency is actually not accidental. It's not accidental because we are reaching a point where competitiveness as a company or anybody depends on how efficiently we can operate our entire infrastructure. And this project that I'm going to talk about is one example of what kinds of things we can do in driving efficiency and what kind of clean slate and completely new systems we can build in trying to get there. By the way, this is kind of a large project we've been doing for the last couple of years. It involves a lot of people, including some interns who are visiting us, like Chia from here, and visiting researchers. And of course, like Vijay and Ming are also sitting here in there. So what's the problem? So the piece of the infrastructure I'm going to focus on is what we call the inter-DC wide area network. So this is the network that connects basically our 5 nines data centers. So our really big data centers, it's a global footprint, and we are talking about essentially capacity along each of those links running anywhere between 100 gigabits per second to terabits per second. So you can imagine this infrastructure is highly critical for our services. It's highly critical because performance of our cloud services depends on it. But at the same time, the reliability depends on it. Every customer write has to be replicated to another data center. So this network is used both for user-facing traffic as well as other traffic in there. Because these pipes are so thick and they run across continents and across oceans, this whole infrastructure is really, really expensive. Vijay can give you the exact numbers, but it runs easily into like hundreds of millions of dollars amortized cost annually in there. So we have this. So what's the problem? This is the problem. The problem is that the current technology stack we have for operating these inter-DC networks, it's highly inefficient. And I'm not talking about efficiency of 80 or 90%. This is actually, even the busiest of links on this network go under 40% average utilization. And most links are actually, don't even talk about it, like 10 to 20% or so forth. So we've invested, basically hundreds of millions of dollars, and we are not able to use it at all because given the technology stack. So why is this happening? So one reason it is happening is that the way these things are, by the way, this is not a Microsoft-centric. Talk to anybody who operates a big IP backbone, and they'll tell you that efficiency is a big problem. Average utilization on the network is a big problem. So this is basically a problem with the technology stack itself, not in the way we run it. So why is this happening? So one reason why this is happening is that in current technology stack, services that use the network, they can send traffic whenever they want, wherever they want, however much they want. So basically, you as a service, let's say a search service or replication service, you send whenever you feel like. It's a good time of the day. The result of that is that the network as a whole goes through periods of peak utilization and really low utilization. So this graph is essentially normalized utilization out of one of our major data centers. And what you see there is that you basically peak around some, this is, by the way, a day-long graph on the x-axis. So you peak around some point, and then you essentially are less than mean, less than a factor of 2 for most of the part. So what this means is that because people are sending whenever they want to send, we have to provision for peak capacity. Because we cannot drop traffic. So now you might say, like, what can you do about this? So this thing is actually not fundamental. So when I talked about like our services, it turns out that all traffic is not created equal. So we have traffic that you might, in simplistic terms, call background traffic. So this is like large replication jobs. And at the same time, we have traffic that you might term as non-background traffic, which is like interactive traffic or traffic with SLA on the order of seconds or minutes and so forth. So as it turns out, you have a mix of background and non-background traffic, and overall this emerges. But if you had the ability to adapt your background traffic, you can actually reduce the peak to mean ratio, which you can basically now use the spare capacity for sending more traffic, or you could actually provision thinner pipes in there. So that's where we kind of headed. So we have the ability, because we control our systems end to end, this offers us a unique opportunity to try and adapt this traffic to the demands of non-background traffic. Here's a second reason. This thing's not working at all. Here's the second reason. The second reason is that the way resource allocation happens in these networks today, it's local and is greedy. So give you an example. If a flow comes from A to E, you figure out a path that you can route it on. So this is MPLS for people who know what I'm talking about. So you get a path from, let's say a flow wants to go from A to E. You figure out the shortest path in the network that can accommodate its traffic. So you pick that one. If another one comes in, basically C to D, because the link C to D is taken, what it will do is basically take a highly local view of the network, and then it will find the shortest path that is left over. If another flow comes in from C to G, what will happen is that it cannot find it because C to G direct link is taken, it will find a roundabout way. So in these numbers, we can run both like simulations as well as do some theory, and we figure out we actually lose like over 20% of our utilization because of these weird effects of local greedy allocation. But the thing is, like, we control our infrastructure, which is this unique ability we have. And if we had a global view, we could actually do a much better job at allocating how traffic flow is routed. So that's an example of it's a much better flow, which frees up actually, not only the paths are shorter, it has also freed up a lot of capacity on the links that did not exist before. So with those two observations, essentially, the goal was to build what we call Swan. It's a software-driven WAN. Our goal is to build highly efficient, and we are putting numbers out there in the sense by high efficiency, I mean that we should be able to run the network with an average utilization that goes beyond 95%. So we are talking average across peaks and valleys, across the day, 95%. That's where we like to go. So it turns out, right, like getting high efficiency in terms of pure utilization is trivial. We have lots of services that could eat up the network in no time. The trick here in this design tends to be, can you actually achieve efficiency while retaining flexibility? And what we mean by flexibility here is that traffic that is high priority should be delivered first, and traffic that is low priority should be delivered later. And so what we do here is basically take basically a survey of the kinds of traffic we have and partition them among strict priority classes, and then we do max-min fairness within a class. So these two key design elements that are part of Swan should not surprise you. They are basically squarely targeted at the reasons behind inefficiency that we see today. So we are going to coordinate the sending rates of services, and we are going to do a global central resource allocation. So how many people here know about SDNs? Okay, so about 30%. So I'm going to do a quick, in case you don't know what SDNs are. SDN is this kind of newish sort of a paradigm in networking. It stands for software-defined networking. The way networks are built today is that we take these big beefy routers from Cisco. Yeah.
I want to clarify.
Yeah.
Are you talking about so you run basically different applications on different nodes, and then they may generate network traffic?
Yeah.
Right? So in this case, do you account for the history? Let's say if you know already that certain traffic goes up and consumes resources at a certain time of day, and you can pre-compute, you can pre-optimize.
You can do, I think you can do.
Could you repeat the question because they need to
So the question is, if we have a historical profile of our services or nodes generating traffic, can we account for that historical profile and set aside capacity? Yes, I think with Swan we will be able to do that, and basically that whole mechanism is called calendaring. So we can provision resources ahead of time.
But I'm trying to understand the problem. In this problem, do you assume having the historical knowledge?
No.
Okay.
No. Yeah. Okay. So the networks today are built using, you take big beefy Ciscos and Junipers, and what happens is that these routers are not only very expensive, the control plane, by control plane I mean the bits of code that computes how flows should be routed, it sits on the routers themselves. So we, as a service provider, we don't control it. It sits right there on board. And the data plane, if you want to control essentially how your traffic is routed, you have to figure out a way to reverse engineer the logic and figure out how can I configure this Cisco router such that the flows patterns that emerge are basically consistent with what I want. So it tends to be, this whole thing, if you try to drive it towards high efficiency, it breaks down really, really fast because you don't have the ability for direct control, and that's what SDNs essentially offer you. What happens with SDNs is you use commodity streamlined switches. So take merchant silicon, buy a switch from Arista or Quanta or somebody like that, and on top of that, you run your control plane on a server. You centralize the control plane, you can write it yourself, and then what you do is you directly configure the data plane of the switches, which determines how flows and packets are routed directly on the switch itself. So that's basically the promise of SDNs, and that's why you see a lot of momentum towards this paradigm, because it gives a lot of control to us to have efficiency and flexible infrastructure. So with this in mind, this is what basically a 10,000-foot view of Swan. We have essentially service hosts generating traffic. They have service brokers. So a service is essentially a collection of hosts. They have a broker. And we have network composed of commodity switches, and they are like network agents between the Swan controller and the switches. What the service brokers, these are representatives of services, what they tell us is how much traffic I want to send between, let's say, Seattle and New York. And at the same time, we are getting information from the network agents. We say, okay, what is the current topology like? How much traffic is flowing on the network or what? So you got your state of demand. So what I'm going to call this like the demand matrix, and that's kind of the network state. Take these two inputs, and you basically, based on your policy, compute how much bandwidth should go to each service. So we've got hundreds of services and hundreds of data center pairs. So we do this allocation for every particular thing, every particular pair, and we compute the exact network configuration that can satisfy the demand matrix modulo our policy. So the interesting bits here is that every 5 minutes, we reprogram the global network. So this is very exciting from a systems perspective. So think of like a network with essentially a global footprint. Every 5 minutes, we completely reprogram it to match a demand. And we see substantial gains in efficiency from being able to reprogram the entire network really, really quickly. So in fact, like every 5-minute delay loses 2 to 3% in utilization, so forth. So we'd like to develop mechanisms that can reprogram the network based on the current demand really quickly. So we've kind of built this thing. And by the way, one certain piece is like the hardest part here in terms of, I think, that does not scale very well is rate limiting. So what we do is push all the rate limiting down to the edge. So the rate limiting is like after services get a bandwidth allocation, that rate needs to be defined. So what that does for us is that what we don't need on the switch itself is any capability to rate limit traffic. All rate limiting would be done there. So the switches can be very, very simple as a result. So I'm not going to go into too much detail about the design challenges, but as you might imagine, while the conceptual viewpoint is very simple, to get this going on that scale, we need scalable mechanisms for computing bandwidth allocation and configuration. We need to work with limited switch memory. One of the reasons those commodity switches are cheap is because they don't have a lot of memory. So can we work within that to actually get the routing we want? The third one, avoiding congestion, that's the one I'm going to talk about real quickly here to give you a sense of the new problems that emerge as we try to roll out this system. And of course, like resilience to failures and bugs. There's a paper coming out. You can look at the details or talk to one of us if you're curious how we do that. Okay, so what's the problem with congestion during updates? And this, by the way, this whole problem emerges only because we are centrally controlling the network from top. This does not happen in distributed protocols, but distributed protocols have other issues. So the problem is the following. Let's say you have your network currently routing the flows as on the left, and you want to route the flows as it's shown on the right. Now the thing is like making atomic updates to, let's say, R1 and R2, which have to determine how flows are routed. It's very, very hard. So what might happen is that one of the flows might move before the other. And when that happens, you basically will have congestion in the network. So think of it this way, Manhattan gridlock, everybody's going clockwise. Now you want everybody to go counterclockwise. Can you do that without actually dropping cars? That's essentially the problem in there. So how do you do that? So, and this is where the nimbleness of the network is guaranteed. So what we do is we create what we call congestion-free network updates. So this is a guaranteed mechanism to change the network from any state to any state without creating any congestion. And we do that by creating a congestion plan or an update plan. So in this case, an example plan is that, okay, don't move entire blue flow at the same time, move half of it, then move FB, and then move FA. And what I missed out here is that the capacity of each link is 1.5 times in there. So this kind of works. So that's the idea. So think of in the Manhattan gridlock example, we have a shoulder, so to speak. And that shoulder is essentially used. In this case, the shoulder is 50%. And that shoulder is essentially used to resolve the gridlock. The interesting things here is that the capacity we provision in the shoulder, let's say it's S, let's say 10%. The number of steps we need in a congestion plan is essentially 1 minus S. So that's a result we can prove. In fact, we can actually find, in most situations, we find like the plan is only 1 or 2 steps. We have some optimal methods for computing the steps. And between 1 or 2 steps, we can change the network state from any state to other. And this is where it kind of gets interesting. Because we have background traffic, the shoulder thing I talked about, you don't actually have to leave that shoulder capacity vacant. Just put background traffic on it. And the loss rate for that traffic we are less sensitive to. So in essence, we are using the roads all the time, except some cars we just nuke when we need the capacity for. That's the kind of. Now I'm going to ask actually Ming to do a kind of quick demo of the prototype that's running in a building not far from here before we conclude. Go ahead. Yeah.
This is the topology. So we built a Swan system, and currently it's being deployed in a test bed that mimic the interdata center topology of Microsoft. This is part of that. So we deploy the servers into 4 locations, and this test bed consists of 8 switches. And we also, the servers generate all-pair traffic between all the data centers. You notice every data center actually have 2 switches for redundancy reasons. So every link between 2 data centers actually composed of 2 physical links. So we run 3 types of application traffic on the test bed. So first one is high priority interactive traffic, which are very latency sensitive. And notice that they are all very spiky. We cannot predict how the demand is generated. The second type is elastic traffic. They are less latency sensitive, but still they have some deadline to make. And the last one is we call background traffic. They have very low priority. Essentially, they are best effort. Whenever there are bandwidth, we want to give them. So So we show the graph here. So the graph on the left, this is a real-time graph. As you can see, the graph is being updated on the right. So the left graph shows the utilization of all the links in this test bed. There are 4 data centers we notice as A, B, C, D. So there are 3 different colors on the links. The red color means the link is highly utilized, and the green means it's low utilized, and blue means it's medium utilized. As you can see, most of the inter-data center links are red, which means they are fully utilized, and only the intra-data center links are green, which means they are not fully utilized, which is what we expected. But what is more interesting is we show on the right graph. So there are 3 time series graphs shows the allocated the demand, traffic demand generated by the application and how much bandwidth the application actually obtains. So for the interactive traffic, even though they are very spiky, so because of the scale on the y-axis, I cannot show it's spiky, but indeed they are pretty spiky. The interactive traffic always obtain the bandwidth request. But for the elastic traffic, as you can see, when the demand grow and increase and decrease, the allocation closely follow the actual demand. And then in the bottom is the background traffic. As you can see, when the elastic traffic demand drop, we give the free bandwidth to the background traffic. But as the elastic traffic demand grows, and we take away those bandwidths from the background traffic. So this is also what we want to achieve.
Just do this. have time. Sorry. Move to the slides.
Just one.
Okay.
So. So I'm also just going to show that we can achieve very high utilization and satisfy the SLA of the application, but we can also react to failure very quickly. So just now, I inject a failure by turning down one link between A1 and D2. So, is there any response? So as you can see, we quickly, within 1 second, we are able to detect this failure and remove the link between A1 and D2 from the centralized traffic optimization. And you can see, even after the failure, all the link can still be fully utilized. And what you can see on the right is, even after the failure, the interactive traffic is not impacted. Only the bottom, the background traffic, their demand actually, they obtain less bandwidth than before.
So what was clear from, I think, hopefully from Ming's demo is basically failure resilience and the flexibility of Swan. What may have not been clear is that how much close are we getting to optimal? So this is a graph taken from real data over our entire network, and what we see is that Swan essentially achieves like 98% of what an optimal method can achieve. Like that's basically not worried about congestion updates, that's not worried about memory limitations, that's not worried about resilience to failures and whatnot. And this is essentially what we are kind of trying to build these days. To summarize, essentially, I think the key thing about Swan, like I said, it yields a highly efficient and highly flexible WAN. It's based on coordinated transmissions across services. Coordination is global, a highly centralized resource allocation mechanism, and we carefully manage how we transition from one network state to the other. I want to leave you guys with the thought that I started with, essentially. I think one of the things that is key and very exciting as a systems person right now is that essentially efficiency is really key. As we build out these really large cloud services, we need to figure out ways to make them efficient. And there's a lot of work, there's a lot of opportunity here in both academia and industry into how we actually make these large cloud scale services efficient. One of the other actually exciting thing for me as a researcher is that because we control these things end to end, there's a lot of opportunity for clean slate thinking. So in Swan, for instance, we are changing the switches, we are putting in some new algorithms, we are changing the servers, we're putting rate limiters. We can do that. And so can, like as academics as well, I would actually like to encourage you to have essentially figure out ways to run the entire infrastructures. Inter-DC WAN is one instance of it, but there's a data center network, there's server efficiency and whatnot, all of those, and you can do that while being not worried about what the current state of the art is, but because, hey, in 2 or 3 years, we'll roll over our entire infrastructure. You know, if servers don't have the capability, if switches don't have the capability, we can do that. So I'd kind of encourage you guys to actually think in that direction. There. With that, I'll end. Thanks.
Any questions? Okay, we're going to have mics. And also, please introduce yourself. So. For the rest of them.
Mark Grichanik, University of Illinois, Chicago. 2 questions. First is, what's the overhead of the software-defined networks?
What do you mean by overhead?
So software, you put it on top of hardware, right? So if you did not use it and you ran the system on top of hardware, then you wouldn't actually have to do additional routing in your software-defined network in the control plane.
So it turns out, I think servers, like we can actually use just one server to do global routing. And I didn't talk about the methods we use to computer allocation. If you're talking about the compute overhead, we can actually use just one server. I think the thing we are more worried about is actually resilience of centralizing computation and not the overhead. Overhead-wise, we can actually deal with it because centralized computation as a whole, it's simpler than whatever the distributed network is trying to achieve by talking to each other. So the key there is like I said, like to just regurgitate, it's like overhead is, in our view, is besides the point. What's more important as we centralize is can we get the same level of failure resilience? And that, I think, we have some techniques, we can talk about that, but that, I think, is an open area in a lot of ways. As world moves towards SDNs, what does the failure story look like? To give you kind of insight in the sense, like in the networking world, there used to be this thing called fade sharing, right? Like the control and data plane used to fade share. So if your control plane fails, you can assume data plane fails. So what has happened now in SDNs is that control plane and data plane are not the same. So now you have to make intelligent guesses around what happens when the control plane fails. Is the data plane up or not? So those are the kinds of issues we are kind of working through right now in there.
Thank you. And second question is about historical data. Do you plan to incorporate it into your decisions that you make in the control plane?
I think I don't know if we'll go historical or not, because I think there's so much flux in our services that historical trends may or may not predict the future. I think what we are seriously thinking is this thing of calendaring, where services tell us not what their current demand is, but they tell us what their future demand is. Because services developers who are deploying the service, they have a better idea. Hey, I'm rolling out a new feature next week, and my traffic is going to go up. So this is the thing that really bothers like the operators, which is like this unannounced changes. Because I think if history was a predictor of future, we'll run a very, very smooth network, right? So that's why I think we'll bring in some explicit signaling from services to actually plan ahead in there. But history, I think, may or may not be a good predictor. So we'll probably stay away from that complexity.
Willis Wanapol from EPFL. You talked about this already, but I have to wonder about this assumption of centrally allocating resources and scheduling flows and stuff like that. Isn't that the Achilles heel of all of this? It seems like an inherently unsolvable problem. What if part of the network gets disconnected from your central resource allocator, et cetera, et cetera? I mean, how are you going to do that?
Yeah. It's a very real worry. I should acknowledge that first. One of the saving graces, though, is that even if the control plane in these networks failed, the data plane continues to function as is. So we go ahead, we program the switches. So in some sense, like commander's intent in warfare, right? So we've told the switches, this is what you should be doing. When the brains go away, the switches will continue doing what they were doing back then. So what we lose now is an ability to handle a major change. It's not like we are losing all traffic in the network. The traffic is just routing when disconnections happen. The traffic is essentially being routed the way it was 5 minutes ago or 10 minutes ago, which is not the end of the world, if we can bring things back up. And the other set of techniques there are, of course, geo-replication redundancy we are using. And I think if network partitions happen, somebody will take over and become the new computer or the new brains of the system.
If I may, sort of another issue. I mean, you're talking on the time scale of minutes here, but is that really fine-grained enough for what you want to do? I mean, there's new applications, flows, thousands of them coming per second.
That's true, but when I say flow, I basically mean an aggregated flow of a particular service between two data centers. I'm not talking about individual connections there. Right.
There was some question in the back, I think. I saw the...
So Gil Zussman from Columbia University. So all of this is running on top of an optical network. So are you thinking about dynamically allocating light path and wavelength in the future?
If the optical folks would give us an ability to program them on a fast time scale, I would absolutely love to use that ability. But today we don't have that. So I think the thing is, like, we can dynamically change how much capacity we have between two DCs or how much link capacity, and I'd personally love that. I think that would essentially, my intuition is that let us drive the efficiency even further, because different parts of the network are under pressure at different times of the day, so we can steal some capacity by.
By the way, some of this is tied to the amount of money they pay for getting a certain kind of bandwidth, right? So you sort of pay that, and we have to meet that. So anyway, there was another question. Raj had a question. I think that'll be last question, because we are at the limit.
So actually, this is a two-part question. First is, you have controllable traffic and you have a non-controllable traffic, which was your high priority thing. So depending upon the randomness of the non-controllable traffic, you really have to allocate the bandwidth. I mean, that part is not controllable, right? So the background traffic has to wait. And you said in the passing that it waits at the edge, which means at the host.
Yeah.
So you have to modify all the hosts?
Do you have to modify all the hosts? Yes and no. I think our current plan would be that hosts that are not modified would get actually put down in what's even a lower priority class, like scavenger class. That's kind of one answer. That gives like how do you go from where we are today to where we want to be. The other is that we can put rate limiters in the operating system or the hypervisor. That's like one place to change without modifying any of the applications. And for some of our services, so there'll be no code changes, and we'll insert essentially a shim that sits in the OS or hypervisor to rate limit. So that's, I think that's a pretty tractable engineering challenge.
Okay, thank you, Ritu.
Thanks.
I was thinking when Vijay was presenting, he said there were 3 pillars. You talked about distribution, efficiency, and performance. So you talked about distribution, Dave talked about performance, he talked about efficiency. So on that note, let's applaud the speakers, and thank you very much for being here.